In this session, we will see about the silt theory and design of canals. So here, if an irrigation canal which draws water from a river carries a certain amount of silt along with the water, which is carried in the bed of the channel, and the flowing of water also occurs the bed and sides of the canal and carries the silt along within it. So under such condition of low velocity, silt is deposited in the bed. So when there is a very low velocity of water, is just because of the silt deposit in the bed, then definitely it is also due to the erosion caused by steep bed, and increased velocity and deposition causes lower velocity and reduced flow area as well. So under such condition, channel is to be designed such that the velocity of flow neither scars nor silts the canal, right? So this non-silting and non-scoring velocity is known as regime velocity, and such kind of canal which supports non-silting and non-scoring velocity is called as regime channel, right? So in the design of canal, the known parameters or the design discharge Q. So the design discharge Q is a known factor here, and the silt factor F, right? And also the rugosity coefficient N. So what is a rugosity coefficient, Ren? I hope you remember that is the roughness of the canal bed, which affects the velocity of water. So even the roughness which is caused by the ripples formed on the bed of the canal, right? So and also that I hope that you remember about the material and the value of yen, right? The material of for earth, masonry, and concrete. The n value varies according to the material. So again, if you wish, then you can check out once the older notes and the lectures which I have given you in the last class, and also that I hope that you're knowing about the silt factor also. So so this silt factor also depends on the mean particle of the silt, right? And also that this factor can be determined with the expression of F is equal to 1.76 root of the mean particle size of silt in terms of I hope you remember it, right? And also this silt factor varies according to the particle uh, of the material, right? So that could be very fine silt, medium silt, coarse silt. So according to that, it varies, right? And also particle sizes, right? So with that varying, the silt factor is purely dependent on them. I think you can also check out these rugosity coefficient and silt factor once again. Go through that part. Okay. So and also that hydraulic mean depth R. So what is the hydraulic mean depth? So I hope you remember about hydraulic mean depth, and also this hydraulic mean depth is also purely dependent, right? So upon the factors of the cross sectional area ratio to uh, the cross-sectional area of flow to the wetted perimeter of the channel. So that will be taken as your hydraulic mean depth, right, which is denoted as R. And so the R is equal to, I hope that you remember, cross-sectional area of the flow divided by the wetted perimeter. So, and also that we know about the velocity of flow and yeah, area of the cross section and bed slope. So we have the continuity equation. I hope you know Q is equal to A into V. You have studied in the fluid mechanics and also the flow equation. The F in the function of N R, yes, right? So the second one, the flow equation, the second one, maybe Manning's equation or Cutter's equation or any other similar kind of a flow equation you can adopt. So if there is the four unknowns are there, then two or more equations must be available to complete uh, the unique solution, right? So and and there is also about and I think you're well aware of the B by D ratio of the fixing of suitable B by D ratio slot, right? So B by D ratio. So I'll just show you in another slide. And so the criterion for this is the first one is that it is not good for alluvial soil where a non-silting or non-scoring velocity is must. And the criteria two is that two and three are utilized by the Kennedy's method of design of channels. So this is the criterion one. So criterion one is the providing channel of best discharging section, thus getting another equation between A and R. Right. So A is the area of cross section and R is the hydraulic mean depth. And the second and third one, that is the limiting equation of velocity from the considerations of scoring and silting, and the governing the slope of the available ground slope. So these two are utilized by the Kennedy's method of design of channels. And the Wood table also shows the suitable B by D ratio for the various discharge. So this is your Wood's normal design table. So here you have the discharge and the relevant B by D ratio and the slope, also the mean value. Okay, so you can have a look at this. So this is how they shall, you can fix your B by D ratio. So coming to the Kennedy's theory. So before that, there are two silt theories, as I said earlier. So one is Kennedy's theory, another one is Less's theory. So the Kennedy's theory is the friction against bed leads to eddies rising up the surface, keeping in the silt suspension. Right. So, and also the silt supporting capacity is proportional to the bed with, the bed width and not the wetted perimeter as it is from sides, uh, which will not support any kind of silt, right? So these are the assumptions which are made for the theory. The eddy's current is developed due to the roughness of the bed, and the quality of suspended silt is proportional to the bed width, and it is uh, applicable to those channels which are flowing through the bed consisting of sandy silt or some grade of silt as the upper valley canal system. So I hope you remember about this canal system, and if you don't well aware of it, then you can search it or let me know. I'll explain you. So, and also you can check for Madhopar Headworks Punjab for the further clarification to know about the Wari Road canal system.